Hello friends, welcome you all to the first lecture on function analysis and its applications. In this lecture, we will discuss on an overview and metric spaces with examples. These are the contents: an overview, metric spaces, pseudometric spaces, examples. These contents will be discussed today. Let us start the topic. What is functional? As we know that the functions or mapping are classified in three ways. First, transformation of second operator. Third, functional. What is difference between them? For example, let x and y be two non-empty sets. Then a rule f from x to y is called function or mapping. If both sets are different, then the functions is known as transformation and denotes the mapping for transformation as f such that x to y. If the mapping into itself, the function f such that x to x is called operator, and the mapping from non-empty set to field, that is the function as f such that x to k is called functional, where k is R or C. R means the set of real numbers and C is the set of complex numbers. In this course, we shall study the analysis of the third kind of mapping from non-empty set to the field. For example, metric, norms, inner product, etc. What is space? A non-empty set with a mathematical structure or function is called space. There are many different types of mathematical structures. This is also known as topologies, including metrics, norms, inner products, etc. And these are known as metric spaces, nonlinear spaces, inner product spaces, respectively. Metric space. So we start here the mapping D such that x cross x to R, where x is the non-empty set. Okay, suppose this is the non-empty set x, and we take any 2 point x and y. So what is the distance between these 2 points? D, that is dxy. So if D satisfies the following axioms, then the order pair xd is called metric space. First axiom is distance between the points x and y greater or equal to 0 for all xy belonging to x. Second condition, dxy is equal to 0. If dxy is equal to 0, it means points coincide. If and only if x is equal to y for all xy belonging to x. Third condition, dxy is equal to dyx, means if we measure the distance from x to y or y to x, that is no change. It means dxy is equal to dyx for all xy belonging to x. xy should be in same domain. Fourth condition, dxy less or equal to dxz plus dzy for all points x, y, z are the element of x. All these points x, y and z should be in x. If these fourth condition is satisfied, then ordered pair XD is called metric space, where dxy is called as distance between x and y. Some authors have written these conditions D such that x cross x to R. In this place, D point such that x cross x to R0 plus. R0 plus equal to 0 and infinity. So distance that is positive. The distance should be positive. Okay. If we write D such that x to R0 plus, then first condition we can omit. If x not equal to y, then distance between x and y should be greater than 0. That is, distance between 2 points is positive. First axiom states that the distance from any point to another is never negative. This property is known as non-negativity. Second condition, dxy is equal to 0 if and only if x is equal to y for all xy belonging to x. It means if the 2 points coincide, then the distance is 0. The property is known as the identity. Third, states that the distance does not depend on the order of the points x and y. That is, dxy is equal to dyx. Here, points doesn't matter. Distance does not depend on the order of the points x and y. This property is known as symmetry. Fourth property, dxy less or equal to dxz plus dzy for all xyz belonging to x. This axiom known as triangle inequality, that is, sum of the lengths of two sides of a triangle is greater than or equal to the length of the third side. Clear? For example, we take real line R. Let R be the set of real numbers and define a function d such that R cross R to R, where d xy equal to absolute value of x minus y for all xy belonging to R. Then D is called the usual metric on the real line R. Explanation: since the absolute value is always non-negative, hence mod x minus y greater or equal to 0. Modulus of the x minus y greater or equal to 0 for all xy belonging to R. So that dxy greater or equal to 0. Hence, first condition is satisfied. Second, if x minus y is equal to 0, if and only if x is equal to y, then it is possible. So, dxy is equal to 0 if and only if x is equal to y. Third condition, x minus y, if we common minus 1, then it can be written as modulus minus 1 and modulus of y minus x. Modulus x minus y is equal to modulus of minus 1 in bracket y minus x. That is modulus of minus 1 into modulus of y minus x. Modulus of minus 1, that is 1. So we have modulus of y minus x for all xy belonging to R. So dxy equal to dyx. Here dxy defined by modulus of x minus y. If order change x and y at the place of x and x is the place of y, then right side we can write modulus of y minus x. So third condition here, dxy is equal to dyx. Okay. So third condition satisfied. Fourth condition, mod x minus y is equal to x minus z plus z minus y. We have here added z and subtract z also. So x minus z plus z minus y, there is no change, and we know that modulus of z1 plus z2 less or equal to mod of z1 plus mod of z2. So using that property, so we can write modulus of x minus z plus z minus y are all x, y, z belonging to R. Therefore, x minus z as per definition we can write dxz and modulus of z minus y can be written as dzy. Thus, the ordered pair RD is metric space. Clear? Second example, Euclidean space Rn. If x is equal to x1, x2 and so on xn, x1, x2 and so on individually in R. Similarly, y is equal to y1, y2 and so on yn. All y1, y2, yn in R. So known as n tuples. Okay. So in tuples we can write x is equal to x1, x2 and so on xn belonging to Rn. Similarly, y is equal to y1, y2 and so on yn are the points of Rn. We can define the metric D such that Rn cross Rn to R as dxy is equal to x1 minus y1 plus x2 minus y2 plus and so on xn minus yn. Then the ordered pair Rnd is metric space. Explanation. Here n terms absolute value of x1 minus y1 plus absolute value of x2 minus y2 plus and so on absolute value of xn minus yn. Okay, so these are the absolute values, sum of the absolute values. So this is positive, that is greater or equal to 0. Okay, so dxy is equal to modulus of x1 minus y1 plus modulus of x2 minus y2 plus and so on xn minus yn greater or equal to 0. Okay, since modulus of x1 minus y1 greater or equal to 0, modulus of x2 minus y2 greater or equal to 0 and so on xn minus yn greater or equal to 0. That is dxy greater or equal to 0. So first condition is satisfied. Second, x is equal to y. If x is equal to y, if and only if x Here given n tuples of x1, x2 and so on xn, and y is n tuples of y1, y2 and so on yn. So x is equal to y, it means n tuples of x1, x2 and so on xn is equal to n tuples of y1, y2 and so on yn. So that x1 is equal to y1, x2 is equal to y2 and so on xn is equal to yn. Okay. From this, modulus of x1 minus y1 plus x2 minus y2 plus and so on xn minus yn is equal to 0, because x1 is equal to y1, x2 is equal to y2 and so on xn is equal to yn, which proves that dxy is equal to 0 if and only if x is equal to y for all xy belonging to Rn. This notation is if and only if. Third, dxy is equal to x1 minus y1 plus x2 minus y2 plus and so on xn minus yn. So these are the absolute values, some of the absolute values. So first term can be written as yn minus x1 plus second term can be written as modulus of y2 minus x2 plus and so on last term modulus of yn minus xn. Okay, as per definition of dxy is equal to modulus of x1 minus y1 plus modulus of x2 minus y2 plus and so on xn minus yn. So this expression can be written as dyx. So dxy is equal to dyx. So third condition also satisfied. Fourth condition, dxy, it is given modulus of x1 minus y1 plus modulus of x2 minus y2 plus and so on xn minus yn equal to x1 minus z1 plus z1 minus y1. Here we have added z1 and subtracted z1, that is x minus z1 plus z1 minus y1, that is there is no change in first term. Similarly, second term can be written as x2 minus z2 plus z2 minus y2 plus and so on. Last term can be written as xn minus zn plus zn minus yn. So this term can be written as less or equal to x1 minus z1 plus z1 minus y1. This is the modulus of the two terms. Okay. So we know that modulus of z1 plus z2 less or equal to modulus of z1 plus modulus of z2. That is, we know that z1 plus z2 less or equal to modulus of z1 plus modulus of z2. So applying this property, we can write this expression in this way. Okay. So x1 minus z1 plus z1 minus y1 plus x2 minus z2 plus z2 minus y2 plus and so on last term also we can write in this way. Okay. So suppose x1 minus z1 plus x2 minus z2 plus xn minus zn plus again z1 minus y1 plus modulus of z2 minus y2 plus and so on modulus of zn minus yn. Okay. So this can be written as dxz. This is the expression of dxz from here dx z and this is dz y. So dxy less or equal to dxz plus dzy. Thus the ordered pair R and D is metric space because all four conditions of metric are satisfied, then the ordered pair R and D is called metric space. Third example, discrete metric space. Let X be non-empty set and the mapping D such that X cross X to R be defined by dxy is equal to 0 if X is equal to Y and 1 if X not equal to Y. Then D is called the discrete metric or trivial metric for X. So how to say the ordered pair XD is called metric space. Okay. So first we have to check the all condition of metric. Explanation: dxy greater or equal to 0 because here dxy defined 0 and 1. So always if x equal to y or not equal to y, then both cases greater or equal to 0. So dxy greater or equal to 0 for all xy belonging to x. Second, if x is equal to y, then dxy is equal to 0, and if dxy is equal to 0, then x is equal to y. Because here dxy is 0 if x is equal to y, and again reverse, if x is equal to y, that is dxy is equal to 0. So this condition for x is equal to y, that is in both way true. For if x not equal to y, then dxy is equal to 1, which is contradiction. Hence dxy is equal to 0 if and only if x is equal to y. Third, if x is equal to y, dxy is equal to 0. Okay, dxy is equal to 0 when x is equal to y. So dxy is equal to 0 if x is equal to y. This can be written as if y is equal to x, then dyx is equal to 0. Both are true. So if x is equal to y, that is dxy is equal to 0 is equal to dyx. If x not equal to y, then dxy is equal to 1, which is also equal to dyx. If point reverse, x not equal to y, that is y not equal to x. That is dxy is equal to 1 or dyx is equal to 1, that is fixed. So we can write dxy is equal to 1 equal to dyx. Hence dxy is equal to dyx. That is third condition of metric is also satisfied. Fourth condition, if xyz is the element of x, if x is equal to y, then dxy is equal to 0. But dxz greater or equal to 0 and dzy greater or equal to 0. That is here only two options, that is dxy is equal to 0 and 1. Okay, so it may be dxy greater or equal to 0, that is 0 or 1, that is greater or equal to 0. So here z is different from x. So dxz greater or equal to 0 and dzy greater or equal to 0. So dxy less or equal to dxz plus dzy. If x not equal to y, then dxy is equal to what? Then z is different at least one of x and y. Hence, at least one of dxz and dzy must be equal to 1. It follows that dxy less or equal to dxz plus dzy. Thus, D is metric for X and the ordered pair XD is called metric space. Pseudometric. What is the difference between metric and pseudometric? In metric, we have 4 conditions. Pseudometric also has 4 conditions, but different in second condition. So, let X be non-empty set, a mapping D such that X cross X to R is called pseudometric. It is also known as semi-metric. For X, if and only if D satisfies the axioms first, third and fourth of definition of metric as stated above, and then axiom 2 we have dxy is equal to 0 even if x not equal to y. In second condition of metric, we have dxy is equal to 0 if and only if x is equal to y. But in pseudometric, dxy is equal to 0 even if x not equal to y. This is the difference. Thus, for pseudometric, we may have x is equal to y. One way can be true. If x is equal to y, this implies that dxy is equal to 0, but converse is not true always. That is, dxy is equal to 0, then x is equal to y. It is not true always. Noting point, it follows that the every metric is pseudometric, but a pseudometric is not necessarily a metric. For example, define the three-dimensional case. Define the metric D such that R cube cross R cube to R. D defined as dxy is equal to modulus of x1 minus y1 plus modulus of x2 minus y2. This is the third dimensional case. Okay, this is x, y, z. Okay, but distance function defined in xy plane, that is dxy defined here in xy plane. So, here x is equal to x1, x2, x3, y is equal to y1, y2, y3, all are the element of R cube. Then D is pseudometric but not metric on R cube. Thus, the ordered pair R cube D is called a pseudometric space. Explanation. Here dxy defined modulus of x1 minus y1 plus modulus of x2 minus y2. Okay, these are the absolute value. So, absolute value always greater or equal to 0. Hence, dxy greater or equal to 0 for all xy is element of R cube. Third condition, dxy modulus of x1 minus y1 plus modulus of x2 minus y2, it can be written as modulus of y1 minus x1 plus modulus of y2 minus x2. So, this expression can be written as dyx. That is third condition satisfied. Fourth condition, for all x, y, z belonging to R cube, where x, y as x1, x2, x3, y, y1, y2, y3. Similarly, z is z1, z2, z3 belonging to R cube. So dxy, here first we have to write x1 minus z1 plus z1 minus y1 modulus of x2 minus z2 plus z2 minus y2. So first term less or equal to x1 minus z1 plus z1 minus y1 plus modulus of x2 minus z2 plus z2 minus y2. That is dxy less or equal to dxz plus dzy. But second condition here failure, because if x is equal to y, then x1 is equal to y1, x2 is equal to y2, x3 is equal to y3. This implies that dxy is equal to 0, because here defined dxy is equal to x1 minus y1 plus x2 minus y2 only. Distance function defined in xy plane. So x1 is equal to y1, x2 is equal to y2 and x3 is equal to y3. Then as per definition, x1 minus y1 0, x2 minus y2 0. For the converse part, we consider dxy is equal to 0, not always x is equal to y. To show this, we consider x is equal to 1, 2, 3, triplet of 1 to 3, and y is equal to triplet of 1 to 5. Then dxy is equal to x1 minus y1, that is 1 minus 1, 0, and plus x2 minus y2, 2 minus 2 is equal to 0. But here x3 is 3 and y3 is equal to 5. Okay, but we can say that x not equal to y. Okay, because third point different. So x3 is equal to 3, y3 is equal to 5. So x not equal to y. Hence dxy is equal to 0 does not imply x is equal to y. So that the second axiom of metric fails. Thus D is a pseudometric. R cube D is a pseudometric space. Next example, let R be the set of real numbers and define the function D such that R cross R to R such that dxy is equal to modulus of x square minus y square. Then D is a pseudometric for R. Proof. First condition, this is the absolute value of x square minus y square, that is modulus value always positive, so dxy greater or equal to 0. Third condition, dxy is equal to modulus of x square minus y square. Okay, so points can be interchanged. So this expression can be written as modulus of y square minus x square is equal to, as per definition, dxy is equal to x square minus y square. So y square minus x square can be written as dyx. That is dxy is equal to dy for all xy belonging to R. Fourth condition, for all xyz belonging to R, we have dxy is equal to modulus of x square minus y square. We have added z square and subtracted z square, that is modulus of x square minus z square plus z square minus y square, that is it can be written as less or equal to x square minus z square plus z square minus y square. Therefore, dxy less or equal to dxz plus dzy. This is the first condition. First condition also satisfied. Second condition, failure. If x is equal to y, then dxy is equal to 0 for all xy belonging to R, because here dxy equal to x square minus y square. So, if dxy is equal to 0 when x is equal to y. But the converse part, we consider dxy is equal to 0, not always x is equal to y. Because if dxy is equal to 0, so we have x square minus y square is equal to 0. That is, y is equal to plus minus x, or x is equal to plus minus y. True. So this we consider x is equal to minus y, then dxy is equal to 0, but here x not equal to y. Thus D is pseudometric but not metric for R. In this lecture, we have discussed the introduction of function analysis, metric space, pseudometric space, and their examples. These are the references which we have used and will be continuously used throughout the lectures. First, function analysis of George Beckman and Lawrence Nairesi, Dover Publications. Second, introductory function analysis with applications, John Valley, written by Erwin Krejcik. Third, function analysis, third edition, New Age International Publishers by V.V. Lemieux. And fourth, function analysis by Walter Rudin. Thank you for your attention.